Information entropy is a measure of the uncertainty associated with the random variable, the message. According to Shannon, entropy is a measure of disorder, or more precisely, it's a matter of unpredictability. For example, if I use a coin, and I have a fair coin has maximum entropy because there's no way to predict whether it's going to come up heads or whether it's going to come up tails on the next flip. It doesn't matter what the previous flips were. Perhaps the next flip has a 50-50 chance. In other words, it has maximum entropy. English text, on the other hand, has fairly low entropy. That's the same as high information content. It's fairly predictable. If you know what the message is about, and you know it's in English, you probably know what the next letter of the message is actually going to be with a fairly high degree of certainty. This brings us to the second law of thermodynamics. It's actually the nature of things in the real world. Order turns to disorder over time. It works that way in wireless when a wireless message is sent. It doesn't matter whether it's sent as a wired signal or a wireless signal. What happens, as you know from Maxwell's equations, the propagation of electromagnetic signals becomes weaker and weaker the further it travels from the source. Like the logo you see here. If we start out with the Notre Dame logo in New York and we transmit it to London, the logo becomes lighter and lighter the further it goes. There's more noise, more perturbation associated with the logo until finally, perhaps by the time it reaches London, we can't even tell what the logo initially looked like. We're unable to clearly identify the signal in the noise. To fix this, we could have amplified the message along the way by having repeaters. If it's an electromagnetic wave, or amplify it if it's a wired-based transmission by having an amplifier built into the wire every so many miles. The first fax machines attempted to get around the second law of thermodynamics in just this manner. But this just helped us identify the problem more clearly. It didn't solve the problem. The unpredictable perturbation of the message is noise. When you amplify the message, you also amplify the noise. Pretty soon, you're unable to distinguish the signal from the noise. There we are with a problem. When you transmit messages over long distances, whether using a landline or, more importantly for us, when you use an electromagnetic wave, the message tends to dissipate. That's where Claude Shannon comes in. Shannon's contribution was to transform the message into binary digits, or bits. How does that solve the problem? Well, the digitized message is a sequence of only zeros and ones, just like Morse code in one sense. It can be repeated and repeated exactly. So now, when I amplify the message along the way between New York and London, what happens is I'm amplifying an exact repetition of the message as it originally occurred. In the real world, we use entropy calculations all the time to make choices. Take, for example, the use of a credit card. When you slide that credit card, a company tries to figure out whether this is going to be a legitimate transaction or an illegitimate transaction. That's why there's always a little lag after you use the credit card before you get your approval. That lag allows us to actually run an entropy calculation. If the entropy calculation shows that there's a high information content that says that this is an illegitimate transaction, your credit card will probably be confiscated. When we classify transactions, that's a binary classification. Binary codes, like Morse code, are also binary classifications. We use them because they work very well in transmitting information. They economize on spectrum. They minimize information loss.